Hello, my name is Kyle Teskey, undergraduate student in mechanical engineering at Cal Poly San Luis Obispo, and I'm working with manufacturing engineering student Griffin Glenn to complete our project, the design and manufacture of a composite backpack frame. Low equipment weight is desired by many backpackers in the ultralight backpacking community. While this may be the case, many users still desire a frame in their backpack for effective load transfer from the fabric bag to their hips, as the packs will be used for long periods of time and carried over great distances. Thus, a solution for lightweight while maintaining effective load transfer is to be desired. Our research shows that the weight of current backpack frames could potentially be reduced by implementing an advanced lightweight material in place of currently used light metals, such as aluminum. Many composite materials have a much lower weight density than lightweight metal alloys. For example, according to Dexcraft Materials, carbon fiber has a weight density that is roughly 54% of that of aluminum, meaning that the weight of a product could be almost cut in half for the same material use. We thus believe that a weight reduction via use of composite materials could be achieved. Furthermore, because of a lack of composite backpack frames on the market, we believe there exists a market opportunity for sales of backpacks with composite frames. The proposed problem for which this project aims to create a solution is that current frames for lightweight recreational backpacks add unnecessary weight to the user's pack. Most backpack frames are currently made of metal alloys and plastics, and composite frames are scarcely found in the market for recreational backpacks. A few select frames have been recently developed utilizing partial composite sections, such as a small back panel which accompanies a larger plastic or alloy frame. However, the market for recreational backpacks lacks fully composite frames, and the fully composite frames that do exist on the market are specifically designed for hunting, firefighting, and other activities in which a high load capacity of the backpack is desired. In contrast to this, ultralight backpackers only need to carry loads up to 30 or 40 pounds maximum, which can be achieved with a less robust and more lightweight frame. For frames to be used in this application, there exists a delicate balance between effective load transfer and acceptable frame weight that composite materials may provide. The ultimate objective of our project is thus to create a successful frame made of advanced composite materials, with the goal of achieving a decrease in frame weight through the use of lighter materials while maintaining mechanical quality. We set out to design a frame that would suffice in performance of mechanical load transfer while using a minimal amount of material. Following design of the frame, an effective manufacturing process was to be determined, and a mold design created for production of prototypes that will be made and tested. A cost analysis was performed as well in order to determine the economic viability of the new composite design. In order to achieve our project goals, we researched composite materials science and manufacturing and discussed these subjects with a composites professor from the mechanical engineering department at Cal Poly to determine the best course of action. Possible frame geometries were designed as 3D models in SOLIDWORKS, and details of the manufacturing plan were determined based upon the design for the frame. The expected weight of the frame was determined using mass property analysis in SOLIDWORKS, and mechanical performance was analyzed using ANSYS finite element analysis. An effective manufacturing process was then determined with consideration of the frame design. Mold design and creation remains in progress, and as a result, prototypes have yet to be manufactured and tested. Once created, prototypes are to be physically tested and evaluated for mechanical performance and total weight. It was decided that the material to be used for the frame would be carbon fiber due to its high strength to weight ratio. Fiberglass was also considered for the design, but was ultimately decided against because it has a higher weight density and is less stiff than carbon fiber. Thus, a frame made of fiberglass would be heavier and more flexible, while the carbon fiber frame is lighter and stiffer. In order to create a more lightweight and concealed frame, we decided on an internal frame style, as opposed to external. The next step was to determine what the geometry of the carbon fiber internal frame would look like. The original design we created consisted of a frame built of hollow carbon fiber tubes, joined together in a rectangular shape that would fill the perimeter of the backpack. This is believed to be potentially the best design option in terms of least material use, but was decided to be unviable for our purposes due to the high level of complexity in the manufacturing process. The manufacturing of hollow carbon fiber tubes is a very complex process requiring advanced equipment that is unavailable to our team, and so we decided against the hollow tube frame for manufacturing purposes. The second alternative design we created consisted of a full-size flat sheet back panel, with the option of adding corrugations to the outer edges of the panel to reinforce the frame. This option was determined to be viable from both a design and manufacturing standpoint, but was ultimately decided against because of weight considerations. The overall size of the frame would be too large, and the amount of material necessary to achieve the desired frame stiffness would cause the weight of the frame to be higher than anticipated. It was speculated that weight could be reduced in this design by cutting out sections of the frame sheet to decrease the total mass of the frame, which led to the third and final design. The chosen design of the frame is a slender sheet with dual semicircular corrugations running vertically on the outer edges of the frame sheet, and a slot cut vertically in the center to reduce the total weight. This chosen frame design is intended to be a composite version of comparable lightweight backpack frames which run vertically along the user's spine. The semicircular corrugations that run vertically on the frame's outer edges utilize principles determined in composite corrugation research in the Mechanical Engineering Department at Cal Poly and act like tubes to provide major increases in bending stiffness and load capacity. Additionally, the semicircular shape of the corrugations has no sharp edges which might cut into the fabric of the backpack or come into contact with the user's body, as opposed to, say, square or trapezoidal corrugations. The geometry of the frame has 15 degrees of curvature so as to better conform to the shape of the user's back, and is expected to be installed in fabric receivers along the center of the back panel, with padding keeping the frame from contacting the user's body. Thicknesses were chosen based on guidance from a composites professor at Cal Poly, with knowledge gained from his experience and previous experimental work with carbon fiber sheets and corrugations. For the style of carbon fiber to be used, a carbon fiber weave was chosen for the material so as to reduce manufacturing complications that may result from improper layup of unidirectional carbon fiber sheets. With the carbon fiber weave, the desired strength and stiffness is expected to be achieved while mitigating risks from improper manufacturing. Manufacturing processes of chopped fiber injection molding and resin transfer molding were considered for the manufacturing process for the frame, but were ultimately decided against. Chopped fiber injection molding was decided against due to the significantly lower strength of chopped fibers in comparison to continuous fibers, and so a method using continuous fibers was chosen. Resin transfer molding was determined to be likely more costly in terms of equipment and thus would require greater initial investment and would not be preferable to compression molding and other considerations. Prepreg carbon fiber was considered as an option as well, but was ultimately decided against due to the cheap availability of wet layup carbon fiber at Cal Poly. This was a design decision made with consideration to our personal project limitations, but may be a more time-effective method of manufacturing for a more large-scale process. The chosen manufacturing method for the frame production is a compression molding process in which mating top and bottom half molds are used to shape the carbon fiber fabric into the desired geometry. The mold is to be made of machinable high-density foam provided at the manufacturing shops at Cal Poly and will be coated with a non-stick primer spray to allow for removal of parts from the mold. Production of parts will require a hand layup of the carbon fiber weave in the mold, thereafter painted with a mixture of epoxy and hardener and compressed in the mold with C-clamps or a compression machine and allowed to cure. A custom mold will be made with a CNC mill and thereafter used for production of the corrugations, while flat surfaces will be used to compress flat sheets for the frame sheet. The frame sheet will then be cut to the desired geometry and the corrugations will be attached in the proper locations with a high-strength adhesive. Finite element analysis was performed to predict the mechanical performance of the frame in the different corrugation sizes. Modeling of the frame was simplified using symmetry, and a single corrugated section was analyzed. Multiple loading cases were identified, and the worst-case scenario of maximum loading was chosen for analysis. This consisted of compression and buckling analyses for a 200-pound load, simulating the loading that might occur if the frame in total were to withstand a 400-pound weight solely along its vertical axis while the backpack were standing vertically on the ground. Results of the analysis showed that the strengths of the two corrugation sizes were comparable, and so it was decided that the smaller corrugation size would be used in order to decrease weight. Based upon the resulting stress values, it was also determined that the frame is expected to withstand maximum loading with a reasonable factor of safety. However, due to the unique nature of composite materials, mechanical prototype testing is necessary to compare the finite element model to, and to ultimately determine the strength of the frame and true factor of safety. Expected frame weight has also been determined using SOLIDWORKS mass property analysis and published values of carbon fiber density. Expected frame weights are approximately 5.5 ounces for a frame with the smaller corrugations and 6.7 ounces for a frame with the larger corrugations. These are much lighter than the 11-ounce composite frames currently available on the market for hunting backpacks and are expected to be lighter than a majority of alloy frames. Success of the manufacturing process and the performance of prototype models are yet to be determined pending creation of the molds. From an initial cost estimation, it was determined that the expected cost per frame for the composite design will be approximately $84, with a total estimated backpack manufacturing cost of $124. As a comparison, the new composite frame was compared to the frame used for the Kelty Red Wing 50, a best-selling recreational backpack that is very popular due to its moderate size and lightweight frame design consisting of an aluminum beam and high-density polyethylene frame sheet. The expected cost per frame for this design is approximately $17 per frame, with a total backpack manufacturing cost of $57. This backpack has a selling price of $140. These numbers show that because of the substantially increased cost to manufacture the composite frame, the current aluminum frame design allows for a much lower price point for the backpack. Further economic analysis was completed to estimate the necessary sale price for the composite frame backpack to make it economically viable. With an assumption of 1,000 units produced and sold each year, it was determined that for a 10-year payback period, the composite frame backpack would need to be sold at a price of $209 in order to be comparable to the existing design. For a 5-year payback period, it was determined that the composite frame backpack price would need to be $211. As shown by the cost estimation and comparison of the existing design and new composite design, the new backpack would have to be sold at a substantially higher price in order to make the product economically viable. It is thus recommended that marketing and sales research be conducted in order to determine if consumers believe the higher sale price to be reasonable and if they're willing to pay that much more for a backpack with the composite frame design. If it is determined that consumers find the sale price to be reasonable, it is recommended that the new design be implemented. If consumers are not willing to pay that price, it is not recommended that the composite frame be implemented. It is also possible that the manufacturer may be able to gain more market share from increased sales of backpacks that use the composite frame and potentially increase consumer base. In this case, it may be beneficial for the manufacturer to implement the new design. Aside from economics, it should be taken into consideration that production of composite frames may have a greater impact on the environment and potentially on the health of the surrounding community where it is manufactured. It is recommended that precautions are taken to ensure that the manufacturing process is carried out in a safe manner. Additionally, material production of carbon fiber is very energy intensive and releases a significant amount of greenhouse gases into the environment. Furthermore, carbon fiber does not degrade, corrode, or fatigue, and thus has a very long lifetime in landfills. These effects should be considered and evaluated and dealt with appropriately. In the end, this project determined that the production of carbon fiber composite backpack frames can serve as an effective way to achieve a lightweight frame design with desirable mechanical performance. However, costs for creating carbon fiber frames via compression molding and assembly are much higher than the cost to create alloy or polymer frames, and so backpacks with carbon fiber frames must be either sold in large volume or at a higher price in order to make the manufacturing of the product economically viable. Further optimization of the design of a composite frame and manufacturing process could potentially be performed to make the process more economical for future models. It's possible that fiberglass or another material could have sufficed and produced a cheaper model, and this is something that would be analyzed in a future design iteration. Additionally, the original tube design could be visited once again. A rough calculation of this design produced an estimated frame weight of just 4.5 ounces. However, the manufacturer would need to take into account the potential for increased cost of manufacturing in order to determine the economic viability of the design. Thank you for listening. I hope you enjoyed this presentation on the design and manufacture of a composite backpack frame.